Alright, so today I'm going to be explaining this important paper with the title DEFT, Efficient Fine-Tuning of Diffusion Models by Learning the Generalized Edge Transform. Dupe edge transform. Of course, the original dupe edge transform is for stochastic processes, slightly different because they work on harmonic functions, different formulation, but in diffusion people still use the same name. They say dupe edge transform. So it's similar. So this paper in NeurIPS 2024 is important because sometimes you have a pre-trained diffusion model. You don't want to go from scratch, and you want to just condition it such that it has some conditional properties. So generative modeling based on denoising diffusion models processes have emerged as a leading candidate for conditional sampling. This conditional sampling in inverse problems. So in real-world applications, we often have access to large, expensive, as I said, we have trained unconditional diffusion models, but we want to improve the conditional sampling using this unconditional. So that's why in their title they say it's a fine-tuning. It's a fine-tuning of that. So most recent approaches are motivated heuristically and lack a unifying framework, obscuring connection between them. Further, they often suffer from issues such as being very sensitive to hyperparameters, being expensive to train, or needing access to weights hidden behind a closed API. So we unify conditional training and sampling using mathematical, well-understood dupe edge transform. Of course, Dupe, I bought his book, very big book, many years ago in England. The title was Stochastic Processes, written by Dupe. And they talk about martingale, super martingale, sub-martingale, which corresponds to superharmonic and subharmonic functions. But this paper is very different from these things. It just uses as a way to control, just like Schrödinger bridge, you want to control the direction of the forward and the backward so that it has the desired marginals that we have, pi 0 at the data distribution and pi 1 at the prior distribution. That could itself be a good distribution, like a blurry version of the images, any distribution. So you don't need to, in Schrödinger bridge, you don't need to start from noise. You start from you can start from any good distribution, and you come up to another data distribution. So they propose this dupe's edge transform, efficient fine-tuning, a new approach for conditional generation that simply fine-tunes a very small network. Of course, they just did it for diffusion, so they can start from noise, but you can apply it for, most people apply this idea to Schrödinger bridge problem. Schrödinger bridge diffusion, and one way of solving Schrödinger bridge diffusion is Schrödinger bridge diffusion matching, like flow matching that you learn the velocity. And so here DEFT, they say, is much faster than existing baselines while achieving state-of-the-art performance across a variety of linear and nonlinear benchmarks. So from theory of stochastic processes, as I said, it's very different. You change the measure. So now we have Q. It has, but we skip from this because that is very different from what this paper is about. So the edge transform gives a way to modify. It just tilt a bit, tilt the dynamics of the diffusion process a bit, so that it samples from the posterior P of X condition on Y rather than just the prior. So we sample from posterior rather than the prior. The authors derive a generalized edge transform that captures many existing conditional diffusion technique under a single theoretically principled framework. So what the edge transform does, if you want samples that match some observation Y, like partially masked image or a measurement in inverse problems, you need the dynamics to follow the posterior. So the edge transform is a mathematical way to tilt the stochastic process so that it end results respects the P of X condition on Y instead of just P of X. So you can think of it like a guiding force that pushes the diffusion trajectory along regions that is consistent with the observation. So your target is this. So for example, the unconditioned one is this. So you just want to tilt it a little bit so that it matches the distribution here, that is pi 1. And of course, we start at pi 0. But the generalized edge transform is that instead of designing a separate guidance term for each condition task, they define a generalized edge transform. So the unconditional, it has this drift and this diffusion coefficient, and this is Brownian motion. So our goal is to sample from P of X conditioned on some observation, like, in images, you do in painting of some part of image, or you have super resolution or inverse problem, depending on your problem. So you need to sample from conditioned version of P of X, not P of X. So what the edge do? So it just, as you see, you just add this, the tilted SDE, instead of just F of X as a drift. Now the drift is extended to have this term as well. So this edge, gradient of edge, is just the guidance. You can think about it as a guidance term that is coming from observation Y. So the term tilts the dynamics so that the process sample from P of X condition on Y. So this is the generalized version. So we can learn, because theta H, first of all, is related to X and Y as well. Not just X, we have Y as well. And we have theta parameter so that you learn it. You know how the tilting works so that we can change it. Otherwise, it's just this drift. And the edge can approximate many forms of conditional guidance. It can be classifier guidance, conditional, denoising diffusion, DDPM, learned conditional drift, Schrödinger bridge formulation, optimal transport like conditional path. So why do we love Dup's edge transform? So if you have F, you have this original unconditional drift, but it edge around allows us to have the guidance to satisfy the observation that we want, because we want to sample from X condition on Y, not just the prior X. So the outline of this paper is that rather than fine-tuning the large diffusion model, so it just first frees the pre-trained unconditional model that you have, then only train a small auxiliary edge of T, so it's very fast. Because it also useful for Schrödinger bridge problem. I've seen many papers like that. Because of so next time I will talk about that, because it takes a long time to talk about that. So the pre-trained diffusion model can be leveraged using Bayes. And then here we start with the forward ST. This is the forward ST, which we go to, which transforms the target distribution, P0. So P0 is our data distribution. So we have this drift term and this diffusion coefficient term. And we denoise it like this. But the goal of conditional sampling is conditioned to reverse ST to a particular observation. So the proposition is that consider the reverse STE. The solution of this H refers to Dub's H transform. It's a transform measure. It's a change of measure. It's a way to change the measure. So in stochastic processes and measure theory, change of measure is very important. Also in computational financial mathematics, this change of measure in optimal stopping theory is very important. So the proposition says that it's a solution, the condition process, this is a condition process, which is a solution of this. Now the drift is B f of t minus sigma gradient of ln of p, such that the law satisfies that. So we refer to conditional process with h sub t and to unconditional process with x sub t. So the unconditional is xt, this is unconditional. The conditional is h sub t. Dub H transform is the conditional, because you are tilting so that it goes in a particular direction that you like controlling a robot to go to a direction that you want. So you are designing the controller. Our controller is here. Now, rather than conditioning an ST on a deterministic event, one is often interested in a posterior arising from noisy observation. So A is just a forward operator. Noisy describes a noisy process. And unlike the classical H transform, we are not enforcing deterministic conditions. So the second proposition says that we recover guidance-based diffusions by this drift. Now, instead of this drift, which is conditional, our unconditional drift is here. So this equation 6, this is the backward STE with marginal PT, because at time t you reach the marginal. So it follows that the backward STE satisfies this law, and we get the guidance. Then the third, the theorem says that it's a representation of conditional STE sampling. So the H transform, the generalized H transform, admits these four representation. You can represent it like a pass measure introduced by H transform STE. You can represent it by admitting as a denoising score matching. I have a playlist for denoising score matching. You can think about it as the following stochastic control formulation. Of course, the optimal solution of a nonlinear controller is Hamilton-Jacobi-Bellman equation, which is a PDE, which is very hard to solve. We solve it numerically. So this fine-tuning, the score matching offers a simulation-free loss to estimate the generalized H transform. So they just use this simulation-free loss using score matching. So theorem 3.1. So while theorem's formulation focuses on learning H transform for a specific measurement, this loss can be naturally be extended and amortized over the full range of measurements. So for DDPM discretization of ST and pre-trained epsilon matching model, the fine-tuning now becomes this simple optimization problem. So you just learn it because it has parameter 5, so you can learn it. So they talk about connection to variational inference and stochastic control. Then they talk about likelihood informed inductive bias in their paper. If the likelihood is differentiable, we can impose an inductive bias on the H transform approximation. So in Appendix 1, they talk about continuous and discrete diffusion formulation. And in Appendix 2, they talk about score, noise, and mean diffusion formulation. But this appendix is important, C1. It's about the intuition of Doob H transform because it provides a formal mechanism for conditioning a stochastic differential equation to hit an event at a given time. What is the probability that it hits this set A? So the stochastic process is coming, suddenly hits. What is the also the nil sets because some of the path don't even go there because they start. Some of them never reach A. So the probability of reaching A for them, for a particular subspace of probability space, is 0. And that's why it's a generalization of probability if you think about it. Because you also care about the null sets. That null probability, zero probability sets. That you never reach a set. So Doob H transform adds a new drift to ST, which amounts to two terms via Bayes theorem, a conditional and unconditional score. So these two terms that I say here for a unique intuition, the Doob's transform ST is a time reversal of the forward ST that is time reversal of forward ST. So it coincides with the Doob transform ST. So we can view Doob's transform as the following series of steps. First, time reverse the ST, we want to condition, impose the condition via ancestral sampling from the condition distribution or posterior. Time reverse, I should create a playlist for ancestral sampling. So the unconditional training of denoised diffusion model is trivial, like very simple DDPM. Discrete denoising diffusion model, I think that model. That paper in 2019, I think it was 2019. But here we have the input is the unconditional train noise predictor. So we perform the reverse diffusion, which is often the Brownian motion. This algorithm number 3 is the core of this paper. That here we want the input is the unconstrained conditional noise predictor function f theta that you use here. This is the estimate noise of sample with noise rest. So the loss is very simple, the true and the prediction. Because you have the non-motive and the motive. Forward noise, the non-motive, and unnoised here, the unnoised motive with noised rest, and set time step on motive part to 0. Then this is the amortized training. We randomly partition data into motive and rest. We forward noise full sampling. We estimate